You ever notice how some things in life just change at this perfectly steady, predictable pace? Like the cost of gas per gallon, or your speed when you've got cruise control locked in on the highway? Well, believe it or not, that predictable change actually has its own language, and that language is linear functions. So, yeah, let's dive right in and see how this all works.
To really get a handle on this, we need to be fluent in its four different forms. Think of it like this. On this slide, we're looking at one single story, a train moving away from a station. We can describe it with words, right? Or we can represent it with a clean little math equation. We could track its progress in a table, or we could visualize its whole journey on a graph. It's all the exact same story, just told in four different languages.
So here's our game plan. We'll start with the basic definition. Then we're going to take apart the machinery to see how it all works. After that, we'll see these functions out in the real world, learn how to build them from scratch, and finally, we'll pack up our essential toolkit.
All right, let's get right to it with that fundamental question. We already had a little sneak peek with our train example, but now it's time to lock in the official definition.
And here it is. The most important thing to remember is that a linear function has two key features. One, its rate of change never, ever wavers. It is absolutely constant. And two, because of that, when you plot it on a graph, you always get a perfectly straight line. Simple, clean, and totally predictable.
Now for the fun part. Let's pop the hood and see what makes this machine tick, We're going to look at the two core components, the blueprint that gives it structure and the engine that gives it power.
Okay, so this right here, this is the blueprint for literally every linear function you'll ever see. F of x equals mx plus b. Now think of b as your starting point, your initial value. And m is the engine. It's that constant rate of change, what we call the slope. If you look at the diver example, it's super clear. The b is the pressure right there at the surface, that's the start. And m is how much that pressure goes up for every single foot they go down. See? The blueprint just perfectly models the situation. So if m is the rate, how do we find it? This formula is the engine that does all the work. It might look a little complicated, but it's just a way of measuring the change in the output divided by the change in the input. In the town population example, we just take the change in the number of people and divide it by the change in years. That tells us exactly how fast the town was growing per year. That's our m. Okay, so we've seen the mechanics. Now, let's take this thing out of the workshop and see it in the wild. Where do we actually run into these straight lines of change in the real world? Well, there are really only three things a linear function can do. It can increase, like the total number of texts you've sent over time, that's a positive slope. It can decrease, like the number of texts you have left in some limited plan, that's a negative slope. Or it can just stay constant, like the flat monthly fee for an unlimited plan, where the slope is just zero. And this is a brilliant illustration of how businesses use this stuff. For Ben's company, that fixed overhead cost of $1,250 a month, that doesn't change. That's our starting value, our B. The production cost of $37.50 per item, that's the rate of change. That's our M. You put them together, and you get a perfect linear function that tells you the total cost for any number of items they make. All right, now we're going to flip the script. Instead of me just giving you the function, we're going to become detectives. We'll get some clues, maybe a graph, a couple of data points, and our job is to figure out the equation. So here's our first case. You see this line on a graph. It tells a story of constant change, right? So how do we translate that picture back into an actual equation? It's actually a pretty simple two-step process. First up, you gotta spot the start. Where does that line cross the vertical y-axis? Right here, it's at -1. Boom, that's your B. Done. Second, you just count the steps to figure out the slope. So from that starting point, how far up do you go for every step you take to the right? Well, we go up 2 for every 1 we go over. You might have heard it as rise over run. That's 2 over 1. So our slope, our m, is just 2. And just like that, we've got our equation. Pretty cool, right? Okay, let's make this case a little harder. What if the visual clues are gone? All you have are 2 snapshots in time, 2 data points. Can we still figure out the full story? Oh, absolutely. Here's the method. Step 1, we use our engine, that slope formula, to calculate m, the rate of change between those 2 points. Step 2, once we have our slope, we plug it right back into our blueprint, f of x equals mx plus b. We can use either one of our original points to fill in the x and f of x values. That leaves only one missing piece, b, our starting value, which we can now solve for pretty easily. And you know what? We can use the exact same detective skills on a table of data. Just look at this plant food experiment. The initial value, our b, is super easy to spot. It's the height at month 0, which is 12.5. To find the rate, m, we just calculate the change in height over the change in months. It's the same logic, just in a different form.
Wow, we have covered a lot of ground, from the basic definitions all the way to detective work. So let's wrap this up by summarizing the essential tools you now have for understanding any linear function you come across.
Here it is, your core toolkit. First, the form. F of x equals mx plus b. That's the blueprint for everything. Second, the formula. The slope calculation, our engine for finding that rate of change. And third, the trends, just knowing that a line can only be going up, going down, or staying flat. With these 3 tools, you can analyze and build any linear function.
At the end of the day, linear functions aren't just abstract math. They're actually a powerful lens for seeing the world. So I'll leave you with this question to think about. What in your own life, your savings, your commute, maybe even your phone battery, is changing at a steady, predictable rate? Because now you've got the tools to describe it.